Hello everyone, my name is Tony and today we're going to be talking about vibration and in particular how vibration causes noise problems in buildings. So depending on what you do, you might be a property manager. I'm sure you've dealt with noisy equipment within these buildings that you're managing. You might be a contractor installing pumps and equipment and trying to avoid these noise issues that you know can happen. So using isolators and different methods. Or you're in the design stage and you're trying to specify what to use or put in details so that you can avoid these problems. All of them come back to the same thing, and that is vibration-induced noise can be very problematic within buildings. Part of that problem is low frequency noise is particularly bad for humans, whether it can create fatigue, headaches, sleep disturbances. It's just bad for our mental health in general. And these low frequencies tend, it's about 20 to 100 hertz, tend to be right in about the range of a lot of the equipment as well. So they can be continuous. Sometimes they're intermittent, which also comes with its own issues. But basically the vibration throughout building is something that needs to be addressed throughout the building's life cycle. And if you want to get a good livable environment for the people who are staying in these places. And what we see quite often is what can be considered a $1 million mistake. And that is that we build these amazing high-rise penthouse apartments, quite often taking up the entire top floor or half of it. And then we put all the equipment right above it. There's mechanical penthouses, there's elevator rooms with all the elevator equipment, and then there's stuff on the rooftop, cooling towers, air source heat pumps. All of it fairly large equipment with big motors that can create a lot of vibration. And it's putting that vibration right in that sweet low frequency zone that I talked about earlier. And so this $1 million mistake is that we've got all this noise going directly into the most expensive real estate in the building. And people who pay that premium expect a premium experience, and that includes the soundscape and the noise within the building. Certain things they're willing to accept. If a plane flies by, they're not going to blame the building for that. But if they hear a constant hum, it's enough to keep them awake. You're going to have no end of problems, possibly even lawsuits. And so this is really what I want to get to in this video. How we can unpack how vibration works, how it starts out as something small, but it might not even be creating much noise, so you don't think it's much of a problem. But then it works its way through the building and it creates a problem. And not always just in the penthouse or in rooms and suites that are close to the equipment. Could even be far away for some reasons that we'll get into later. And what I would like you to take away from this is that these are very solvable problems. It can be expensive if you're retrofitting, especially if it's large equipment or something that you don't want to shut down, like an elevator. It's definitely better to address it, at the design stage. But in a lot of cases, these noise problems that we hear, particularly from equipment, are vibration induced. And that's something that I really want everyone to take away from this, because mistakes get made. A lot of money ends up getting spent if you go down the wrong path. All right, so let's get into the three main sources of noise in any building. The first one, it's pretty obvious, that's airborne noise. That's people making noise. Maybe they're in the next room watching TV or listening to music loudly or speaking loudly. Could be cars or airplanes outside and coming through your window. Construction activity out in a neighboring property. That's all airborne noise. It's the noise that we can hear, and then it's getting through your walls or windows, or maybe your windows are even open, and they're coming into the area which you don't want that noise. And noise being unwanted sound, essentially. We talk about unwanted noise, but I think most noise is typically unwanted. And airborne noise is actually has the least amount of power. So it's generally easy to deal with, but it does take architectural solutions, because you can't isolate airborne noise very easy. It's not coming from a single source generally, or one that you can control. So your problem there is that there's no way to isolate airborne noise. But it doesn't have a whole lot of power, because it's going through the air through compression waves, and those compression waves are what generate some vibration that gets into your structure, but it's fairly weak. And then the next main source is vibration-induced noise, and that's what we are going to be talking about today. Vibration-induced noise is when mechanical energy is injected into the structure itself, and that's usually with any kind of mechanical equipment or perhaps some electrical equipment. that creates vibration, and you attach it to your structure. And as soon as you do that, that energy, there's no way for it to dissipate at the source because it's hard connected, and that energy will get into your building. That's the next very common source of noise. And that needs to be dealt with at the source. And it can be very problematic because it travels through buildings very well. And there's a lot more power going directly into the building compared to just regular acoustic noise, because that equipment's got, if it's a large piece of equipment, will have quite a bit of horsepower in it, and there's any offset in that rotation will create your vibration, and it can do it with a fair amount of power. That's why you want everything well balanced, and hopefully it doesn't create a lot of vibration, although some equipment just does by the nature of its design. And then lastly, we have impact noise. That is generally going to be footfall. You get this problem in a lot of apartment buildings and condo buildings, especially wood frame buildings, because people's heels come down and they hit the floor, and it can create quite a bit of impact, and you hear that clunking sound, that banging of footfall on the floor. And that's the most common one, although any kind of impact, people dropping things, shutting drawers and doors, things like that, are all impacts. And again, this can actually, even though the sound itself is brief, it has the most power, because you're getting a lot of power just driven right into the structure upon impact. And so impact can be very difficult, because it's also similar to airborne noise, generally hard to isolate at the source, because the source is, like airborne noise, quite often the source is people walking around. You can't isolate them necessarily without addressing the structure itself. So those are the three main sources, and like I said, I'm going to be focusing on vibration-induced noise today, and I'll look at airborne noise and impact noise in another video. Okay, so how does this vibration work its way through the building? What are the structural dynamics and some of the vibration isolation principles so we can mitigate this? So I don't want to get too deep into the woods, but there's a few things we need to talk about here first. First of all, is frequency, and that's measured in hertz. And if you are unfamiliar with it, this is the number of cycles per second of that vibration. So how many times that vibration goes back and forth within a second. Then there's displacement. That's how much that vibration causes the equipment to actually move. And that displacement depends on how it's mounted. And that displacement, if it's hard attached to a structure, will also take place in the structure. So you might have that displacement in the floor, and that's where your vibration problems occur. The next is velocity, which is the speed, typically measured in meters per second. And last but certainly not least, acceleration, which is meters per second. And acceleration is monitored very closely, because this is usually where a lot of the problem comes from. The higher that acceleration of your structure, the greater a problem it's going to cause for noise. And so this is the one that you see when there is vibration testing. If you're working with equipment, typically what you really want to look at is that acceleration, although the velocity and displacement also play a role, and definitely the frequency, but that acceleration is really what drives it. And so that's what we look at most closely. All right, and so within buildings, we also have an issue that we have with all structures, and that is the phenomenon of resonance. Resonance is the natural frequency of a system. So if you're thinking of a guitar string and you pluck that string, it's the frequency that string just naturally will play at. And most components in a building will have this, especially if it's structural things like beams or concrete slabs, windows. They all have some sort of natural frequency that will get them going more than other frequencies will. So what you're trying to avoid is matching a structure-borne frequency that's coming from vibration with the natural frequency of the structure itself and of the finishes and the things that will be within a suite or an office, because that's where the noise is going to be created from that resonance, or created quite highly. And because of this, you find it can be difficult to track the path, because a resonance might not occur until quite a distance away from the actual equipment itself. And so it does cause some confusion sometimes with noise issues, because the resonance might be in a suite that's 7 floors above the equipment, where floors 1 through 6 don't actually have the same issue. It's just finding that resonance in a pipe or the walls or something in that area. So even though the power of that vibration will dissipate over distance, it's still creating more noise a further distance than a closer distance. And this is a fairly common phenomenon. So energy transfer, and how you can mitigate that with isolators. So what we tend to use, and you see a lot in the industry, is a spring isolator. And the reason is it's got a very low dynamic stiffness. And what that means is you can compress a spring. Once a spring's deflected, it will move and compress without any real damping. You see damping. When you want to think of damping, think of a car. You've got, if you look underneath your car at the front wheel, you have a big spring and a shock inside of it. So the spring, that's what allows the movement. It allows the tires to bounce up and down so that it doesn't go into the car. But the shock system inside of it, it's the damping, so it doesn't just bounce and bounce like you might see in an old car. It's one of my favorite scenes in the movie Uncle Buck, actually. Uncle Buck's driving down and his car bounces up and down for about 30 seconds. It clearly has no shocks whatsoever in it. And yeah, that's what would happen if we didn't put shocks in cars. And so you get these two phenomenons depending on how you're isolating. Typically, if you're using spring isolators, you're trying to avoid any damping because the damping will put more energy back into the structure. And in most cases, you don't want that unless you're really trying to control the movement of the equipment itself. Then you would want some damping. But a lot of cases, that dampening is going to work against you as far as vibration isolation is concerned. Where you do get some damping is in rubber isolators. And that's why typically a rubber isolator with the same deflection won't isolate quite as well as the spring because that damping is going to work against you. And when you isolate right there at the equipment, what you're looking for is an isolator that's going to give you a good isolation efficiency. And that isolation efficiency is the amount of energy that actually gets through the isolator and down into the structure. So if you're looking at say you had a 2-inch deflection isolator on a fan that rotates at 1500 RPM, you're going to get something well above 99% isolation efficiency. So what that means is 99% plus of that energy is dissipated by allowing that object to move and convert that energy into kinetic energy and let it dissipate. Only 1% or less is actually going through the spring and getting into your structure. So, in most cases, that's probably enough. Some it might not be, because if that particular piece of equipment was really powerful, that 1% still might be too much. But that's how isolation efficiency works. There's different ways to calculate it. There's a simple single degree of freedom, which is used for kind of basic things. But for more complicated equipment, particularly heavy equipment that's got enough weight that actually deflects the structure, then you get into calculations with 2 degrees of freedom. Neither one's that complicated, but the problem with the second one is you quite often don't really know what the building is deflected by. So it's hard to calculate the second one. First one's pretty easy, and we use that quite a bit, at least to give us a ballpark if this is the right piece of equipment, the right isolator or not. And to demonstrate kind of, how little power it takes to amplify noise, a trick we quite often use is the music box. So you wind it up, there's very little power in a music box, right? Just a little spring that spins this little cylinder around. And we've got Edelweiss, or at least a version, out-of-tune version of it. And so that plays, it's got so little power. It's just flicking these little tiny metal tines, and that's the power, that vibration. So that energy, which is very insignificant, when you put it in a little box, will get amplified, and that's like your structure. And to demonstrate that, you can hear this, if I move it away, it should get a little bit quieter. But if I take this and I mount it down on a plate on my desk, you can see what happens is that the plate, like the structure, it's, in particular this plate, it's got a very stiff mass that's got a lot of smooth surfaces, similar to a window. And so when you add that little bit of vibration to the plate, it will amplify it. And so that's where isolation efficiency really comes in handy, important when you're trying to figure out exactly what you need for a piece of equipment. That efficiency needs to go up. The the more vibration comes from the equipment. The more power it has, the more off balance it is. Different types of equipment have different issues. You really got to take that into account, not just when you pick your isolator, but where you put that equipment, because that isolation efficiency, it can't, you're going to have to get higher and higher levels, maybe even use air springs when you have equipment in or close to sensitive areas. So if we have the fan that's running 1200 RPM, we want to make sure that the natural frequency of the spring under deflection is no more than a third of that, right? So 400 RPM, or better yet, 300 and a quarter. And what's important to remember, it's not just the rated deflection. You look at the sheet and it says, oh, this is a 1-inch deflection. That deflection only matters if the load actually deflects that spring by 1 inch. So it's not just the deflection of that isolator. You've got to make sure that actual load and weight are on the isolator, and you can see how much that isolator compresses. That's your true deflection, your actual deflection. So if you oversize your springs, you might run into trouble because you end up hitting that natural frequency or getting close to it. And if you do that, your equipment's going to bounce around and you're going to have bigger noise problems than you had when you started. So it's something to take into consideration. You should always match as closely as you can the rated capacities to your actual loads, because then you're going to get the deflections that they're rated for, and the numbers that they're actually touting in that literature will be true. I see this a lot with pads, because you might have quite often you have like just a little 2-inch by 2-inch pad will be good for 150 pounds, say. And so if you got 4 of them, that's good for a piece of equipment that's 600 pounds. So if you put a small piece of equipment on a big pad, you think, oh, I'll just put a pad underneath this whole thing. If it doesn't deflect very much, you're not going to get a great isolation efficiency. Luckily, with rubber, because of the damping, the issue of getting into resonance isn't nearly as bad as with springs, but still, it's not going to be effective. So you want to really look at matching your loads to what the isolator can handle, what its capacity is, to get the rated deflection, and therefore get the isolation efficiency that you're looking for. Okay, so now that we know that this vibration is getting into the structure, how is it creating noise when it gets into another room? And that's caused because the vibration will get into all the different objects. And if it's they're called bending waves as it goes through something like a wall. And that bending wave's actually moving that wall, and that movement is what's creating compression waves in the air, which creates the sound. Now, not all equipment will transmit efficiently. This really depends on what's called the coincidence frequency. And this coincidence frequency is when the speed of the bending wave matches the speed of the compression waves in air. Because in air, it doesn't matter what the frequency is of the sound, those sound waves will travel at the same speed. But in a solid object like a wall, those bending waves don't. They move at different speeds depending on the frequency. So the coincidence frequency is when that speed within the bending wave matches that of air. And that's where you're going to get an amplification of noise. So if you can avoid that coincidence frequency, your noise is going to be a lot less. Unfortunately, there's very little way of kind of addressing that, because windows are what they are, walls are what they are. They're going to have a certain frequency depending on these different, depending on the frequencies coming into it. They're going to have a different coincidence frequency. And so there's no way to really judge that. Again, it goes back to isolation. The best way to deal with vibration is to eliminate it as much as possible at the source, because you can avoid these coincidence frequencies or these resonances throughout the building that you really have no way of doing anything about at this point anyway. You might at the design stage, but even that's fairly complicated. It takes a lot of modeling, which we do with larger buildings, but in most cases these are things that you just have to deal with, and they're not something you can really manage. All right, so how does this vibration get through the building and cause sound in the first place? How does it, go from a pump room 6 floors away into the suite and cause a lot of noise? And what's happening here is in your structure, as I was saying earlier, what we're dealing with there is our bending waves, our flexural waves. So unlike air, where you're creating with compression waves, we're actually creating different pressure zones essentially that moves through the air. Bending waves, they actually ripple the object that is creating that wave. So if you think of a pipe and vibration traveling through the pipe's actually sort of rippling as it's creating a bend. It's going through that object. And you can see that like on a guitar string. If you were to slow it down, the string kind of bends as it moves that wave along the string. So this is the path, and this is how it moves through your building, and it will follow those flat long paths really well. And so it can go through concrete beams or pipes or ductwork, most of the things in the building, unfortunately. And so these paths, as they connect from structural component to structural component, will work your way through the building. And there are certain things that will help. If that pipe takes a turn, for example, it actually will allow the pipe to move, and it will kind of change the direction of that bending wave, which takes away from some of its power. Also, you have mismatch impedance anytime you go from one component to another. So if you go from steel to concrete, some of that energy will be reflected at that point. And so it will slowly mitigate over distance, but it can travel a long ways, especially, like I said, through something like a pipe or a duct that is it's very stiff, but it's also flexible. And so it can travel through that flexible object. And that's why pumps tend to be a little tricky, because they can send vibration through a building through its piping system and travel a long distance. And then when it gets to that room, it's either going to find a resonance, or it's going to find that coincidence frequency and create noise in that room. So vibration doesn't respect room boundaries. It can go from room to room just by going through all these different columns and then switching over to wood if it's a wood structure, and it just radiates throughout. So this is why you really want to watch how well you isolate your equipment, because that little hard connection is what gets you every time. So, and this is something I see a lot here in BC, because we have seismic codes and have to deal with the potential earthquakes. So everything needs to be bolted down. But of course, as we talked about before, bolting it down is how you transfer energy right into your structure. So spring isolators that you install on equipment here in BC all have to be seismically rated, which means that the housing itself will stop the equipment from going anywhere. But in operation, the housing actually isn't touching anything. Everything's just free floating on the spring, so that you don't have a short circuit of that isolation system. And where I see this go wrong a lot here is with rubber pads. Rubber pads, they're sort of like your entry-level vibration isolator. They don't have a lot of deflection, so they're not going to give you a really great isolation efficiency generally, and they have some inherent damping because they're rubber, so they wouldn't be as good as a spring. However, they get used a lot on equipment where we're not looking for a lot of isolation. But what happens quite often, in my experience in the field, is that then someone comes along and just bolts them down. And now you've created an acoustic short circuit, because that vibration, instead of going through the pad, being mitigated by the pad, maybe 70 or 80% of it getting down into your structure, you're letting the vibration just bypass the pad, and it'll go down through that bolt, which is completely rigid, especially if you crank it down. So that's like that pad was never there in the first place. And this is something to avoid in all systems. So it's the same with a piece of equipment that's isolated on springs. It might be isolated great on those springs, but if there's some other component that goes hard back to your structure, it'll just follow that path. Now, it might not be as bad as if it was just sitting on the ground, but it will create another path, and sometimes that's all it takes. Especially, like I said, we've seen this with pads where you bolt them down too tight and they just don't work. You take those bolts out, suddenly your isolation system's working again. All right, now let's get into some of the most common noise creating culprits and some solutions. So one I've already talked about quite a few times is pumps. Pumps can be bad because they have a rotational imbalance. They have fluid in there, which, not just moving air, which is a lot lighter. They're, moving typically water. And there's hydraulic pressures. There's pulses that pass through the piping that can also send noise, like through the water, not just down the skin of the pipe. And so they have a lot of vibration and a lot of avenues for that vibration to get into the building. So the solution for pumps, especially if they're larger ones, is one, to use an inertia base. It helps because the pump itself's got a lot of movement. You add an inertia base, it just makes the pump itself, in a sense, heavier, which means it's going to have less amplitude and it's going to have a better ability to absorb that energy just by trying to move that base. Another big important part of any kind of pump installation is to isolate the piping. And so the best standard is to use like a double sphere rubber connector. They work the best just because that vibration has to get through quite a big thick chunk of rubber before it can continue on down the path. So you get some energy loss when it transmits from steel into rubber and then back from rubber into steel through mismatch impedance. And you get an isolation system with that rubber connector. Now, having said that, they're not perfect. They're still, the spheres in it will take out some of that pulsation in the water as well, but vibration still will travel through that pipe. Just, it'll be reduced at that point. So the other thing I always recommend is to use spring hangers on your piping as much as you can. So if you're in a mechanical room and your piping goes up to the ceiling and then over to through the hole where it's cored through to another room, put a spring hanger in all those locations and a flex connector, because what this does is it allows that piping to move. It allows it to move, dissipate energy before it gets anywhere where it's hard connected. So the further and longer you can isolate your piping, the better. And it also helps to have turns. The more 90-degree turns there are, the more it'll allow that pipe to be a flexible system. And again, it will release a lot of that energy. And another culprit I see quite often are like heat pumps for HVAC systems. They're similar to pumps. They've got compressors, and the compressors rotate fairly high frequency, and they've got a lot of movement because they're a compressor. And they've got like a piston system inside. So that creates a lot of imbalance, which creates a lot of vibration. So unfortunately, you see these. I've seen them where they install them on every floor to run their HVAC system. So those can be a big problem. You have to deal with them in a similar way that you would pumps. Ideally, inertia bases help, but definitely you want to get them on spring isolators, 1 or maybe 2-inch, depending on the situation. And any type of connection coming off of it should be isolated, whether it's piping, and similar to pumps, if you have piping coming off of it and it goes up to the ceiling, get that on some spring isolators. Allow that movement to happen as soon as possible before you hit any hard connections. That will release the energy through movement and stop it from getting into your structure. And one I deal with quite often, it's a little bit different, are elevators. They, because they're intermittent, they start and they stop, they can be very disruptive to sleep. And they can be quite difficult to isolate because the elevator, the people installing them, they don't want them to move. They want their elevator system to be very rigid so that it works to their tight tolerances. Unfortunately, that also means they're going to create a lot of noise. Depending on the type of isolator, the ones where you've got the machine in a room, they're much easier to manage. But what you see, especially over time, is they'll put them on pads and the pads will stiffen or degrade over time. Or they're just put in pads that are, quite frankly, too stiff to begin with. And so going back to what I said before, you want them on pads, but also you want to make sure those bolts, because you're always bolting down these elevator machines, are not going to short circuit those pads. So you want to make sure you're using a double nut and you're not tightening down and cranking down. Otherwise, your vibration is just going to travel through the bolts. They also have noise, from the rollers and the ropes running over the shivs. All these things can create noise, although the machine is typically the one that's the most severe. Now, another one that we seem to overlook quite often is transformers. Now, I think maybe the reason is that they don't have motors inside, so they don't have rotating, the movement that we associate with the vibration. However, they do have what's called magnetostriction, and that creates similar type of vibration. And you get these hums that are tonal, and they're constant because you don't turn off your power transformers. They just run as long as the power is going through them. So unless the power goes out, it's a non-stop, usually about 120 hertz. And of all the different noises, this one seems to really drive people crazy. So it's one to watch out for. If you're getting just a 120 hertz hum in your building and it just doesn't seem to stop, 24 hours a day, it's a good chance it's a transformer somewhere causing it. And in this case, it can be quite complicated because of the way power transformers are installed. Typically, we use neoprene waffle pads, but if that's not enough, they can also be put onto spring isolators with a great deal of care because of you want to keep steel away from certain parts of the transformer. But it is sometimes necessary to put power transformers on spring isolators. Otherwise, you're going to get these real tonal noises at around 120 hertz that people find very, very disruptive, particularly to sleep. Okay, so as a final takeaway, really you should be addressing vibration at the design phase. It's so much easier if your equipment's installed properly, if it's on spring isolators that are actually floating, if your piping is on spring isolators, you've got flex connectors in the piping, et cetera, et cetera. It's so much easier. So at the design stage, that's really where a lot of this should be happening. Don't put heat pumps, big noisy heat pumps, hard bolted on every floor of a hotel. I've seen that. Don't do that because you're going to have problems. In the case of the hotel, you're going to have rooms you can't even rent because there's so much noise going through them. So at the design stage is where a lot of this should be done. It's costly to do retrofits, especially if they're structural, if we're replacing walls or putting in sound clips or ceilings. It's all going to cost a lot more if you wait till that stage. Having said that, it's going to happen. So it can be done. Call your professionals, get them out, take a look at it, and come up with the design. It may cost a bit, but in the case of that hotel, it will be worth it because you actually be able to rent these expensive rooms out. Or in the case of a suite, you'll be able to rent them or have some people live in them. Anywhere where people sleep is going to be a problem if you've got vibration noise in that room because it's probably somewhere tonal, it's annoying, maybe it comes on and off, it wakes people up. So get it at the design stage, but if you don't, it can be dealt with. So I encourage any of you, if you have a noise problem and it sounds like it's coming from equipment, really look at that vibration path first. I find a lot of people make the mistake of thinking it's acoustic. And, I don't know how many times I've gone in a room to see something that's causing a lot of noise. You go into the mechanical room and they've lined the whole thing with egg crate foam, which is good for reducing sound within that room, but it really doesn't do anything as far as that vibration leaving the room or even sound for that matter. So look at that vibration path first because that's probably what's going on. You're probably looking at a vibration-induced noise issue. And if you follow that path, you might find some solutions without hiring a professional. And if you have to, that's fine too. So leave some, if you have any of these stories, please leave them in the comments. I'd like to hear it. And thank you for listening to it. Subscribe if you can. And I will be putting out some more deep dive content on architectural acoustics in the future. Thank you.